We're now going to take a look at our second case in our partial fraction decomposition. If you recall, in case 1, we looked at what to do when our denominator has only simple linear factors, right? Now, in case 2, we're going to still assume that our rational function, which again is just a quotient of polynomials, is proper, right? So that means the degree of the numerator is less than the degree of the denominator. And now we're going to say that q of x could possibly have, so q of x has repeated linear factors. So things like perfect squares, perfect cubes, and so forth, right? And, just to kind of give you a sense of what we mean by this. So for instance, let's say, you have 2x plus 1 cubed, and I ask the question, what are all the factors of 2x plus 1 cubed, right? Well, the thing is, even though this is a convenient way to write it, sometimes when you write it in this form, you lose sense of really what's going on. And what's going on is it's a product of, these binomials, and they're all repeated. They're the same. So in terms of, all the factors, what are the factors of this? Well, here are the factors. 2x plus 1 by itself is a factor. Okay. And then if I take 2x plus 1 times itself, so 2x plus 1 squared, that's a factor, right? Because again, it's a factor in the sense that these expression can evenly divide this expression. And then, of course, 2x plus 1 cubed, all three together could evenly divide it, right? So with this in mind, it kind of gives us a sense of what to do in general when you have a factor that's repeated with a certain multiplicity, right? So let's write down the general rule. So if q of x has a repeated linear factor, and it's of the form ax plus b to the m, and then our m would be greater than or equal to 2. Again, that way it's at least it's a repeated factor with multiplicity 2, but it could be a lot higher. So if our denominator has such a factor, then the partial fraction decomposition must have the following terms. Right? So what should we include? Like how could we break that big, fraction down to smaller fractions? Well, the smaller fractions must look like this. You would have a constant over the factor raised to the power 1. So you'd have the ax plus b to the first power. And then you'd have to have another separate term where you take the factor to the second power. So then you take the ax plus b to the second power. And again, that would have possibly a different constant on top. And you keep going until you get to that power of m, right? So then you'd have a sub 3 over ax plus b cubed, and so on until you get to that largest power, right? So again, we don't know what that power is. The description here is, in theory, giving us a method for whatever multiplicity, right? But in practice, when you're doing these problems by hand, the multiplicity might be 2 or 3, right? All right, so that's what it looks like when we have a repeated linear factor. Now keep in mind that this case 2 could show up in conjunction with the case 1. So you could have a single polynomial that has maybe a couple factors that are repeated and some that aren't, right? In fact, let's take a look at an example that will illustrate just that fact, right? So let's say we have to perform this anti-differentiation. So let's say our function is 10x cubed plus 3x squared minus 17x plus 5 all over 3x to the fourth minus x cubed with respect to x, right? And again, just a quick check, we see that the function is proper. The degree in the numerator is 3. The degree of the denominator is 4, hence it's proper. So we can proceed, right? Now, if you take a look at the denominator, the 3x to the fourth minus x cubed, usually when we factor it, well, we think of it as x cubed, factor out an x cubed, and we're left with 3x minus 1. And that's fine. But many times when you do this, you might look at this x cubed and say, no, this isn't linear, but this is cubic. But what you're missing is the fact that that x cubed really can be factored further. In fact, that's what that fundamental theorem of algebra says. It says that if any polynomial of a certain degree can be factored as a product of linear factors or irreducible quadratics. So we don't have any quadratics here, but all 4 factors are linear. It just so happens that these 3 are repeated, right? So these are repeated linear with multiplicity 3, and then this one is a simple linear. Simple just meaning that factor shows up only once, right? And this is what case 2 tells us how to handle. All right, so let's write down what the general form of the decomposition should look like. In other words, here's this big kind of a monstrosity that we have to integrate, and we want to break it into its smaller pieces. So the 10x cubed plus 3x squared minus 17x plus 5. And let me go ahead and write the denominator as the x cubed times 3x minus 1. And our PFD says that, well, let's handle the simple linear first. So we'll have a constant over 3x minus 1. And now let's handle the repeated x's. Well, the process says first you take one factor of x, you put that as a separate fraction. Then you take the 2 factors of x, you put that as a separate fraction. And then now you take all 3 together and you make that, now we have 4 fractions in our decomposition. But the thing is, whether or not the factor is repeated, right? The PFDs of all of these, right? The simple linear and the repeated linear, they only allow for constants in the numerator, right? So in this case, the problem really boils down to finding these constants A, B, C, D, right? And we have a process for that, because once you write down the decomposition, the process for finding the constants is very similar, right? Okay, so let's clear our fractions. So let's take this denominator and multiply both sides of this identity. So we're going to be left with the 10x cubed plus 3x squared minus 17x plus 5. if I take this denominator and multiply the first fraction, then the 3x minus 1 goes away, and I'm left with x cubed times the a. So I'll write it as ax cubed. Then if I take the x cubed times 3x minus 1 and multiply the second fraction, then this factor of x will cancel out one of the factors here, and I'm going to be left with bx squared times 3x minus 1. And just keep going. Again, take this denominator, multiply the third fraction, then the x squared will cancel out two of the factors here. So I'll be left with c times x times a quantity, 3x minus 1. And then finally, if I take this denominator and multiply the fourth fraction, and the x cubed goes away completely, and I'm left with b times the quantity 3x minus 1. All right. So now what we're going to do is we're going to use that second method for figuring out a, b, c. Oh, why did I write a b here? Let me fix this. So that's minus 1, and then plus d times the quantity 3x minus 1. So now we're going to use that method to figure out a, b, c, and d. Let's expand these and collect all the like terms and see what we have. So we got our 10x cubed plus 3x squared minus 17x plus 5. Now if you look closely, we only have an x cubed. Well, let's see. We have an ax cubed here. And let's go ahead and distribute this, so we'll have a 3bx cubed minus bx squared. Let's distribute the cx, so we have a 3cx squared, and then minus cx, and then finally 3dx, and then a minus d. All right. So again, let's group all the like terms together. All right. And it's in problems like this where you start to see the benefit of this other approach of essentially collecting all the like terms and then matching up the coefficients. So for the x cubed, we have a plus 3b times x cubed. For the x squared, I'm going to write it like this. We have a negative b plus 3c times x squared. And then for the x term, I have a minus c plus 3d times x. And then there's only one constant term here, and that's the minus d. Right? So we have this. So now what do we match up? Well, the coefficient of x cubed on the left-hand side is 10, which means it has to be equal to the coefficient of x cubed on the right-hand side. So that a plus 3b has to be equal to 10. What about the x squared? So the coefficient of x squared is 3. The coefficient of x squared on this side is a negative b plus 3c. Those are going to be equal. The coefficient of x on this side, we can't forget the negative, so it's negative 17. That's going to be equal to the negative c plus 3d. And then this is the really helpful part. Since there's only one constant term here, so negative d is going to be equal to a positive 5, right? So if we start with that, we automatically know what d is. So let's write that down. So negative d is equal to 5. So therefore d is negative 5. Then let's match up the things in red. So the negative c plus 3d, that has to be equal to negative 17. But I know what d is, so I can just plug it in here. So this tells me that negative c minus 15 is equal to negative 17. Add 15 to both sides, so negative c is negative 2, so therefore c has to be 2. Here we go. Now let's match up the greens. So the negative b plus 3c, that has to be equal to 3. But now I know what c is, so I can plug it in, and I get that negative b plus 6 is equal to 3. Subtract 6 from both sides, I get that negative b is equal to negative 3. So b is equal to 3. It's looking good. And then let's see, and then the blues. So let's match up. So now then we would be able to know what a is. So a plus 3b is equal to 10. And let's see, so a plus 9 is equal to 10, so therefore a has to be equal to 1. Right? So in fact, the algebra that we ended up doing here wasn't quite as messy as the previous one. It just depends on the function and the case, really. But what we can say is, I can now write down the partial fraction decomposition with the constants that we just solved for. So we have 1 over 3x minus 1, and then b is 3, so we have plus 3 over x, and then c is 2, so we have plus 2 over x squared, and then d is negative 5, so then plus negative 5 over x cubed. So integrating this, right, or our original, is equivalent to integrating this, right? So let's actually do the integration. I mean, there's a lot of work that goes into the partial fraction decomposition, but that's not the end of it, right? We do have to do an integral. So we have to integrate 1 over 3x minus 1. That's going to be an ln, but we're going to have to be careful how we handle that coefficient of 3. And then we have plus 3 over x, that's another ln. And now to integrate the other two, right, these are no longer going to be ln because I have to interpret them as power functions. So this is 2 times x to the negative 2, and then minus 5 times x to the negative 3. Right? And this is what you have to be careful in the repeated case, because now you have like your factors that are raised to powers that aren't equal to 1, and that's because of the repetition. So even though these two are going to be ln, these are not going to be ln antiderivatives, right? So let's write down the antiderivative here. So we know for sure that it will be ln, so ln of 3x minus 1, but in order to reverse the chain rule, I have to divide by that coefficient that's in front of the x, right? And that's a process that we've seen several times now, not just with ln, but we've seen it with the exponentials, we've seen it with the trigonometric functions, right? And then plus this one, we would imagine factoring out the 3, and then we're left with the antiderivative of 1 over x. Well, that's our natural log, right? So these two are natural logs, and now let's apply our power rule. So add 1 to the power, So it becomes -1 divided by -1. So we have a -2 times x to the -1. Power rule again for this, add 1, so we get -2 divided by -2, so that's plus 5 halves, x to the -2, and then we have our plus c, right? So if you want to write your final answer without negative exponents, this is what it looks like. So we have 1/3 natural log of 3x minus 1 plus 3 times the natural log of x. This will be minus 2 over x. So the 2 doesn't get reciprocated. It's only the x that you take the reciprocal of. And then same thing here. The 5 stays in the numerator, but the x squared ends up in the denominator. So it looks like that, plus c. If you wanted to rewrite it in such a way that you combine the logs together into a single log, this is what it would look like. This first logarithm, bring up the 1/3 power, so you'd have the ln of 3x minus 1 to the 1/3. Bring up this 3, and you'd get the ln of x cubed, right? And then the other terms just come down. And then you can write this as the cube root of 3x minus 1. But now since you're adding these two logarithms, apply the property where the log of a plus the log of b is the log of a times b. Right? You could do that, and there we go. So a lot of these, these are just extra steps depending on how much you want to simplify or combine your logs. You could get a common denominator if you wanted. But again, all of this is really algebra, and I think we've probably done enough algebra in these partial fraction problems. So hopefully case 2 is not too bad, with the repeated roots. You just have to remember that each power of that repeated root has to end up being its own separate denominator. All right, see you in the next video.